So we've spent a long time in this lecture talking about different sedimentary processes. We focused a lot on weathering before, but now we're going to get down into the nitty-gritty of the erosion and transport, of deposition, and of lithification. So as we look at this collection of sediment, we know that it has been weathered off of the rock that it starts with. And over time, the sediment will change in features as it weathers, but it also gets moved elsewhere and it gets laid down somewhere else. In the process of moving that material away from where it starts, and then transporting it through other environments, there are going to be changes that happen to those minerals, some that we've already talked about. The weathering process continues. Let's talk about the difference between erosion and transport. So erosion is the initial movement of weathered sediments away from their source. And I like to distinguish this from transport because it turns out that water, sometimes it can pick up stuff, sometimes it just moves stuff that it's already picked up, and sometimes it leaves stuff behind, depending on the energy of the environment. We've already mentioned that. Transport, we distinguish from erosion because it's the movement of sediments by a transporting medium through places that were not the source of the sediment. In this class, I'm going to distinguish them. You won't always see them distinguished, but I like distinguishing them because when you graph the types of particles that are transported or eroded or deposited, you see that they're different. Let's think about this graph over here for just a second. What we have is the velocity, the speed at which water moves. So this is, right, a proxy for the energy of the environment from low to very high energy. And then on the x-axis are the sizes of sediments that can be moved, transported, that can be eroded, picked up even if they're not transported yet, or deposited, that get left behind. So at the very lowest energies, really slow moving water, it can transport clay that it's already holding, but it can't actually pick up any clay because it's not moving quite fast enough to do that picking up. And that's why I distinguish erosion and transport, because eroding it, picking it up and starting it moving is different than just keeping it moving. Really slow moving water might contain clay, but it leaves behind all of its silt. So that's why something like a floodplain, you'll get lots of silty sediments left behind because that water is moving real slow. And so it leaves behind all of its silt. It might carry away some clay, but if you left it long enough, still, even that clay would settle out. At faster speeds, it can transport clay, silt, some sand, but it can't even really pick any up because it's not moving quite fast enough. Even moderately moving water won't be fast enough to pick up new sediments because they're already sitting there. You need to add some energy to get it going, and water of this speed just doesn't have quite enough. At the fastest energies, you can erode all types of particles. You can erode some clay, you can erode some silt and sand, and even some gravel if you're moving very fast. At super fast speeds, everything gets moved. Right? These are huge flash floods up here. Somewhere in here is rivers, depending on their morphology. And we'll talk more about that in this course. But the faster moving rivers are up here. The slower moving rivers are down here. And then this is something like floodplain or the open ocean. Some folks also distinguish this process called mass wasting from erosion. Mass wasting includes things like landslides. That's an example of mass wasting. It involves movement of what is initially a consolidated, right, an often combined, an often large volume of material all at once. So it's sudden, it can be catastrophic. Landslides are a real danger. And mass wasting is unique because it's kind of like you start it moving, you move it just down slope, and then you leave it in a pile where it's behind. So you erode, you transport it, you deposit it all at once. So it's related to erosion, but it's also transport and deposition. Erosion, on the other hand, involves more gradual transport of clastic debris created by weathering processes away from its source. Show you some pictures of a particular mass wasting event that occurred in the late 90s in Venezuela, killed tens of thousands of people because all of this sediment suddenly started moving at once. You can see this whole city really buried by all of this debris. And look at the size mixture in some of this, right? These are the size of cars down here, huge boulders, meaning that the water must have been moving very fast that transported them all the way down the slope. Yeah, some of those boulders, 300 tons. Like, you're almost surprised that some of these buildings stayed standing with the boulders moving, running into them, I'm sure. And certainly there were some buildings that were destroyed by these. Now, what can trigger a landslide? It can be water. So water from upslope somewhere in this area probably took all the sediment and just started moving it down slope and dumped it all in this house all at once. How does that work? Well, if you take water and you fill in the spaces in between sediments called pores, you can start to suspend those sediments so that they're not in contact with one another. Normally, when it is just dry enough that friction is still holding these together, the sediment's not going to move. But if you add just a little bit more water or a little bit of motion to water-saturated sediment, those sand particles, the sediment particles, will no longer be in contact, and you can get them all moving at once, which is one way in which landslides can all suddenly occur because all the sediment will start moving at one time. So what else can trigger landslides? Very steep slopes can be a factor. Gravity is really pulling hard on all of the stuff that's making up these steep slopes, and there's not a lot supporting them underneath. So just a small change then on these steep slopes will cause them to catastrophically fail and cause a mass wasting event. This is a picture taken from a place called Earthquake Lake in Montana. It was a very recently created lake. It's just to just be a dammed river. So you can see, right, the trees that used to just be living on dry shoreline. So how did this lake form? Well, this earthquake-driven landslide, earthquake happens, destabilizes the slope just a little bit, and it all falls down and creates a natural dam in this valley. It also killed almost 30 people at a campsite nearby. Just to give a sense of the geological risk that comes with these landslides. As I mentioned, earthquakes can cause or can promote landslides because they just jostle stuff enough to get it moving. So here we see evidence from a rock avalanche on top of a glacier. So this is ice, right? This is a glacier. And rock has cascaded down in a mass wasting event and just sort of spread out over this whole glacier. Another thing that can promote landslides is sparse vegetation. So if you have vegetation on a spot, its roots hold it in place. So if you have very sparse vegetation, you don't have roots holding that in place. And over time, you can start to get enough motion promoted that these can slump sort of all at once. So you can see the land surface just slumping because we've removed all the trees from this spot and there's only a little bit of scrub holding it in place. So to distinguish that from more gradual sediment erosion and then transport, you can look at something like a river that's always moving. Looking at this river, we can tell that it's got a lot of sediment in it of various sizes, probably clay, silt, and sand especially, because it's not moving too fast up here. We can tell because it's so turbid and brown that there's a lot of stuff dissolved in this water. I will note that whenever you see waterfalls like this, or like this back here, you've got something different going on in the river channel itself, where you've got a lot of transport, sediments being moved around. If they're big enough and the water slows down enough, you might get sediments left behind, versus what's going on right at the waterfall. At that waterfall, you've got a whole lot of motion going on all at once, right? This is all driven by gravity. Water is pulling it from upslope to downslope. And at that very edge, you've got a lot of energy contributing to erosion of that material. So this waterfall and this waterfall are both ultimately moving back over time, because erosion is happening very severely at this spot, whereas on either side, it's mostly transport. Down here, transport. That's also why you can just make out some really big rocks and boulders at the base here, but why they don't continue as you go further down slope, because they all get left behind here. The water is super energetic right here. It can erode all sorts of things, any size. Then once it gets to here, the water is just flowing at the typical speed of a river. It can't support the movement of a boulder anymore. So if you've ever watched how rain moves across a flat surface that's missing too much vegetation, you've seen that rain will start to move as sort of a flat plane across that surface. It doesn't immediately form channels, and we call that sheet wash. But over time, as it finds slightly lower places, which it's easier to move to because water is naturally flowing downhill because gravity is pulling it that way, it starts to preferentially enter those small channels. And that's another positive feedback loop, because as the water goes into those channels, it all moves in that direction, and that expands the channel and makes it so more water can move and expands the channel some more. So you very rapidly form these channels. First, and most prominently, down at the base. And then later, that erosion sort of moves up headward as more and more water fills in behind it. And so that process is called headward erosion, where the erosion first starts further down slope where the water is concentrating, but then that erosion actually continues back upward toward the headlands, or the start of where all the water comes from. This is very similar to how erosion works on a broad scale, on a landscape scale as well. And in fact, in places that are called water gaps, a lot of times what has happened is headward erosion of that old stream here has cut away and cut away and cut away until it actually cuts all the way through a mountain. And it can even capture old streams that are there and introduce them into its own flow. That's what creates things like the Delaware Water Gap, and some of the other gaps, like Cumberland Gap that you might know in Tennessee, are created by this process. Just erosion working over time. Now's a good time to bring up for the first time what a watershed is. We'll see it again when we talk about stream morphology, but I do want to point out that a watershed is the region that is drained by a stream. And those are separated by drainage divides that run along the highest topography in between two watersheds. So stream A would drain all of its watershed over here. Any rain that falls over watershed A is going to end up in stream A at some point. Similarly, any water that falls in watershed B is going to end up in stream B at some point. And these areas are separated by a drainage divide. So we've been talking a lot about erosion and transport by water, but it turns out that transport by wind can happen pretty easily as well. So this is a picture from the US Dust Bowl that occurred throughout the 30s, where because you had a lot of drought and crops being destroyed, you didn't have a lot of vegetation holding the sediment making up the soil in place. And then because of increased winds that were in the area from various changes, that sediment was able to be picked up by the wind and just blown across the landscape, scouring things as it went, making it hazy, having health effects on people, and making the soil less fertile overall. That wind transport is responsible for dust from the Sahara, actually, so the Sahara, right, being the desert in Africa, which is off the map, way across the Atlantic Ocean to the east here. That dust is actually blown all the way across, reaching the Caribbean, reaching Central and South America, reaching as far as the Amazon rainforest, simply blown by the wind. This stuff called loess, or lurse is how that's pronounced, is the name for unstratified sediment deposited by wind. And usually this stuff comes from glaciers grinding rock over time. It's kind of like, originally it's like flour that's been created by glaciers just grinding rock over thousands and thousands of years. And then wind that's whipping around near those glaciers is able to pick up that dust and sediment and deposit it all over the Great Plains of the US. That's what creates so much of our fertile soil, actually, in the United States, is this loess that's covering a huge part of the central and western United States. That all was created originally by glaciers and transported by wind to where it sits today. Wind can also move particles about as big as sand is just about the largest particles that wind can move. And oftentimes it sort of bounces across the landscape. It doesn't all get picked up all at once, although in really big sandstorms, it can pick up even sand particles. But that general wind in dunes, over time can move that sediment around and is what created those cross-bedded patterns that we saw in that intro slide and that we see here. So let's talk a little bit about deposition now. So this occurs when the transport medium no longer has the energy to support the sediment being transported. If the energy decreases, the water or the wind slows down, it drops some of its sediment load. High energy environments that stay very high in energy will leave behind only the largest particles, the hardest to move particles, whereas low energy ones leave behind small sediments. And as we saw before in that first sub-lecture of this part, that's what connects our observations of grain size in clastic sedimentary rocks to the environment in which they formed. It's really the energy present when those sediments were deposited. There are three ways that sediments can move. We've talked about dissolved ions when we were talking about chemical rocks. But then there's two ways in which solid particles can move. They can be suspended, especially clay particles, but also smaller ones when moving fast, that are actually, they're held up at all times by the water flow. But then there's also the bed load. Those are particles that aren't necessarily being picked up by the water, but that are being scooted along the base, that are being rolled or bounced into each other. And if those particles sort of bounce and they hit and they bounce and they hit and they bounce and they hit, we call that, we have a special name for that called saltation. Grains collide into each other, give them some kinetic energy, more grains fly up, those go down slope, all transported by the flow of water. So we've got bed load, suspended load, and dissolved ions are the three varieties of sediments. So which factor below is the most important in controlling the size of the largest rock that can be transported by a stream? Which do you think is most important? And remember, we're trying to tie one of these to energy. I think width is most important, or depth, or length, or the slope of the stream channel. Which one determines how much energy the stream has? You might be familiar with mountain slopes being much, or mountain streams being much faster than meandering streams, and that's because the mountain streams have steeper slopes. The rate at which water can move, pulled by the force of gravity and countered by the drag being exerted on it by the landscape, is primarily controlled by this slope. So that's the most important when it comes to figuring out what can be transported and what gets deposited or left behind. It's that slope of the stream. Shales being deposited. If clay particles align themselves, if they settle out and are able to align themselves in these flat layers, all pointing in the same direction, they will form a shale. And we call it a shale because it is a rock mostly made up of clay-sized particles. And the other important part of the definition of shale is that it has prominent layering, or this fissility. It breaks into these chips very easily that you can see here. Now, if those clay particles, those same clay particles, let's say they're dumped out and they don't have time to sort of settle and align themselves, they will form mudstone instead. That mudstone doesn't have any chippiness to it, so it doesn't have fissility. An alluvial fan is a special type of deposit that we talk about a lot that shows a lot of the properties that we've been talking about in terms of deposition pretty well. We don't run into them out east much because these tend to only be preserved in deserts. There isn't a ton of vegetation obscuring things. Here we see an image of a place in Death Valley where there used to be a highway, right, running along here. But there's a narrow mountain stream, and occasionally, every several years or so, you'll get a big flood because you get a lot of rain at once, and all that rain washes down the slope and it concentrates in that valley. And in that valley, it can move cobbles and boulder-sized particles. It's a flash flood, so it can move huge particles very fast. But once that stream, or that mountain valley stream, opens out into this much broader valley here, continuing it up to the mountains that are outside the image to the bottom, it all slows down at once. There's no longer a steep slope that it's running down. It's no longer channelized. And so the water spreads out into this fan-shaped, right? I think you can imagine it being a fan with a handle down here. That's why we call it an alluvial fan. And the water fans out and dumps all of its sediment load very fast. And it can dump sand and gravel-sized particles, but it's very poorly sorted because the velocity of that water changes very rapidly from when you go to here to here. The velocity is essentially none once you reach that far out in the fan. So just dump everything right away. As you go further, it's all silt and clay and probably evaporate deposits even. So we've made it all the way to the last process in forming a sedimentary rock. That's the general process of lithification. It's a process by which loose, unconsolidated sediment, like he's holding, turns into a solid rock. So how do we take sediments and stick them together? It involves a couple of things. So burial is going to help all of these because burial is going to put pressure on it. Which forces the sediments to stick together a little bit. Well, it forces them really to be in closer contact, which is what compaction is. So compaction is when pore spaces decrease due to pressure on the rock. Burial also promotes what's called cementation because you can be subjected to groundwater flow, which has lots of dissolved ions in it. Cementation is growth of new minerals which stick the rock together. So compaction and cementation, both promoted by burial, are what lithifies or turns a rock from a pile of sediments into a solid rock. This is essentially what answers this question. After sediments are transported and buried, right away they're not going to be consolidated, but over time these processes are going to be able to act. And we've talked about compaction and cementation. By squeezing out all the water that's there, you allow the grains to become much more in contact with one another, and the only spaces are going to be these small pore spaces filled by water. Cementation is the growth of new minerals from ions or from the sediments that are there, sort of weathering in place and adding stuff to solution. And those new minerals, as they grow, will lock these sediments in place as well. Combination of compaction and cementation is what allows lithification to happen. So here you can see a thin section image of what a sandstone looks like on a microscopic scale. These rounded sand particles that are made of quartz have been cemented together by minerals that have grown in between. This calcite that has grown and sort of stuck these rocks together, these clasts together. So calcite is a common mineral that acts as a cement in sedimentary rocks. Another thing that helps them stick together is that when you put pressure on it and you're compacting those sediments together, if you put enough pressure on them, you can actually sort of get them to fuse together at the borders. Those grains will deform slightly and they will start to lock together a little bit. You can even see a little evidence of that pressure acting because it's broken this one grain in a couple of spots. Here's a microscope image of sand grains that were otherwise round being cemented together by growing carbonate minerals. In this case, some dolomite that's growing right on the surface of both minerals at once. And as it grows, it's sort of bonding these two together, just like cement would. Another mineral that often contributes to cement is clay. So quartz tends to stick around, but remember, as things like feldspars and other silicates weather, to form clay, those clay minerals can actually grow in place and stick these quartz together.